welcome to the Saint Wilfred YouTube channel. I am Mr. Satyendra Kumar and going to present a topic over here, that is instrumentation amplifier. Means how we can use an operational amplifier as an instrumentation amplifier. So this is an application, instrumentation amplifier using an RTD bridge. So this RDT or RTD, temperature dependent resistance, are there, and a bridge, usually a Wheatstone bridge, is taken having an RTD or a temperature dependent resistance in a particular arm, which will sense the temperature and accordingly will produce will change its value, and so the voltage across it will change, and that voltage we need to pick it out and amplify through an instrumentation amplifier. So this is just an application. First we need to understand the bridge. So let us understand the bridge, which is usually a Wheatstone bridge. Let's see, we have a DC supply over here, VDC, and there is a bridge consists of 4 arms. Out of these 4 arms, we have to choose a particular arm with a temperature dependent resistor, say it RT, and connect this particular to this particular node. Now this node say VA, this node say VB have been taken out for the input of instrumentation amplifier. And here is your output with respect to ground. Okay. So first of all, we need to find the value of VA and VB, or the difference between VA and VB. Whenever the bridge is balanced, then VA will be equal to VB, and at that particular condition the output voltage will be equal to 0 volt. But whenever this VA will not be equal to VB, this V out will not be equal to 0. That means you will have some voltage over there, and that is corresponding to the voltage difference created due to change in this particular resistance. So say at a particular temperature, all these resistances, say RA or RC, RB, RA, RT, whenever, according to the Wheatstone bridge, whenever this RB upon RC will be equal to RA upon RT, then this bridge will be balanced. And if the bridge will be balanced, the VA will be equal to VB. Okay. Now we have chosen this particular RT at certain temperature so that all these resistance will be equal. In such case this condition will be met, and if this condition will be met, then VA will be equal to VV, and so the output voltage will be equal to 0. Now let's suppose if the temperature changes. If temperature changes, then corresponding this particular resistance will get changed, and so we will use a particular change in resistance value, that is delta R. Either it will be increase or decrease according to the temperature variation. So this resistance will change while all these three resistance will remain same. Therefore this bridge will become unbalanced, and we need to find the expression in unbalanced situation, what will be the value or difference between VA and VV, and this instrumentation amplifier will just amplify the difference between these two. So let's calculate the value of voltage VA. If we are calculating this particular voltage VA, so what will be the circuit diagram? Let's see, we don't have this particular input lines. If we don't have this particular input lines connected to the instrumentation amplifier, in such situation these can be assumed as open circuited. Okay, so if so, the value of VA will be equal to VDC, total voltage applied, divided by the total resistance RB plus RC, and multiply by this particular resistance across which you need to find the voltage, that is RB. Similarly, VB will be equal to applied voltage VDC divided by the total resistance across this particular arm, that is RA plus RT plus minus delta R, which is the change in resistance due to change in temperature. Okay, and multiplied by the resistance RA across, we need to find the voltage. So these are the two expressions, equation number 1 and equation number 2. We have the value of VA and VB in unbalanced situation. Therefore the difference between VA and VB will simply VA minus VB, that is VAB is equal to VDC upon RB plus RC into this RB minus VDC into RA divided by RA plus RT plus minus delta R. Okay. So if RA is equal to RB is equal to RC is equal to RT at certain temperature, then VDC into, say it is R 1 upon twice R minus 1 upon twice R plus minus delta R. Now you can solve it out. as VAB equals to VDC into R multiplied by twice R plus minus delta R minus twice R divided by twice R into twice R plus minus delta R. Fine. So this will get cancelled. Ultimately you will get VDC multiplied by R into plus minus this delta R divided by twice R into twice R plus minus delta R. So this will be the value of VAB at temperature different than this particular RT, this particular temperature. If the temperature changes from T, then the value of this particular temperature dependent resistor will change by delta R, and correspondingly we will have a change in voltage VAB across the bridge, that is terminal A and B. So this will be the equation number 3rd. Now we have the next section as instrumentation amplifier. So the circuit diagram of instrumentation amplifier is, we will use a buffer at the input stage of this instrumentation amplifier, plus minus minus plus. Here is your VA and VB, which we have calculated over there, that is the difference between these two is VAB. We have this from the equation number 3. Now we are using a buffer amplifier. That means the output of this amplifier will be same as the input. So over here we will get VA and here VB. Now we will use a comparator circuit or differential amplifier, say a differential amplifier like this. So this particular circuit diagram, simply it will, here you have the VA and VB. So this, why these sections has been used over there, what are the importance, and what will be the output or gain of these two stages of the instrumentation amplifier, we can compute it simply. As these are the buffer amplifier, means whatever the value will be available over here will reach at this particular point. How? So it is, if you think about this particular circuit only, think about this. What is? It is a kind of non-inverting amplifier. So what is the output of non-inverting amplifier? VB, say VB dash, as we have used over here VB, so VB dash, and that VB dash will be equal to the gain of this non-inverting amplifier multiplied by the input VB. Now what will be the gain of this non-inverting amplifier is 1 plus RF by R1. What is the value of this RF? Is 0. So if it will be 0, the whole value 1 plus 0 divided by anything, that will be 1. So it is 1 cross VB, ultimately you will get VB. Means whatever you will have over here will be the same at VB dash. and that's why I have assumed it as VB, and this is called a buffer amplifier. You may ask why we use this buffer amplifier if the voltage at this particular input terminal is same as this particular point. The reason is this buffer amplifier provide an isolation between input and output. If there is any back EMF to the input, then that will not propagate to the input due to this particular amplifier, and so for precaution we are using this buffer amplifier. Means input is isolated from the output through this particular buffer amplifier. Sometimes we just use it to contain the input value. Now this VA and VB come over here, VA and VB, okay, and we have to define the next section, second stage, as a differential amplifier. What is the gain of a differential amplifier? We have already studied it as V out is equal to minus RF by R1. That means RF, we usually say it RF, feedback resistance, and this particular resistance or this one resistance R1. So whenever we use this particular formula, or we take the value of R1 is equal to R4 and R3 is equal to R2 and R3 is equal to R4, in such situation the gain of this particular second stage or differential amplifier, gain of differential amplifier, that is second stage, is equal to minus 1. And so the output will be simply equal to VA minus VB with negative sign. Now if the input due to change in resistance is not much larger, is not a useful value, in such case we can change the gain of this particular amplifier so that we will have a large output over here. So how to change this particular value? For that we need to change in the buffer stage. Let's see how. Or we can change this particular gain. We have the two options. Usually the designer has changed the gain of this buffer stage as see, we are assuming it as VA dash or VB dash. Now the value of VA dash will be VA dash minus VB dash will be different than the earlier one. How? Say this one resistance is RX, RY and RZ. Okay. So if so, the current through this particular branch is 0. Current through this particular branch is 0 because there is no current through the input of this differential amplifier, as the input resistance of this particular op-amp is infinite. So this will be treated as open circuited, and therefore the current through these two branches will be 0, and in such situation this will again act as a buffer amplifier. Whatever the input will be equal to the output, or if we will use over there, this value will be equal to, as using virtual ground, this is VB, so this will be VB, this will be VB, it is VA, so this will be VA. According to the concept of virtual ground, this will be VA, and if so, the current through this particular branch will be equal to that is say it is Ig. So what will be the value or Ry, Iy? What will be the value of Iy? It will be simply equal to Va minus Vv, voltage difference between these two terminals, divided by this resistance Ry. So this will be the current. As the current will not go through this branch, so the whole current will travel from this particular point to this point. And therefore the difference between voltages across these 2 points, that is Va dash minus Vb dash, will be equal to this Iy, as it will remain same to this branch to this terminal to this terminal. So Iy multiplied by the total resistance, that one is Rx plus Ry plus Rz, and therefore from above equation it is Va minus Vv divided by Ry multiplied by Rx plus Ry plus Rz. Fine. Vab dash. And therefore this value is obviously greater than the value of VAB. That means whatever you are sensing your resistance will change the value through delta R. If that particular voltage difference created due to this particular change delta R is not sufficient, in such case this particular gain will amplify those changes and you will have the large output at your output of the instrumentation amplifier. Further, you can increase the gain through the second stage of instrumentation amplifier. If the gain of second stage of the operational amplifier remain 1, the final gain will be this one. V out will be equal to, if the gain of next stage will be 1, if the gain of a difference second stage is equal to 1 or minus 1, in such case V out will be equal to VAB dash, that one is the equation, VAB divided by RY multiplied by RX plus RY plus RZ, and therefore the gain, that is V out divided by VAB, which is input voltage, will be equal to Rx plus Ry plus Rz divided by Ry with a minus sign, and as the gain of the second stage is minus 1, so minus has been applied over here, and it will be finally, if now you can also consider it, take another consideration, Rx is equal to Rz, then this will be simply twice or equal to Ry, let's say equals to R. In such situation, that one is 3R divided by Ry, so gain will be simply 3. If not, then whatever the value you will have, you can use them. Sometimes the Rx and Rz are made equal to reduce the effect of noise, and in such situation R plus Ry plus R divided by Ry, so you may write it as minus of 1 plus twice R upon Ry. So some book has been derived this particular expression for the instrumentation amplifier, some are derived as we have derived it previously. So this is all about the instrumentation amplifier. Now why we study these particular operational instrumentation amplifier, what are the usage of this instrumentation amplifier is that whenever we need to apply or measure a precise value of particular, say we have to measure our pulse. Say we have to measure our pulse. The voltage generated through this particular pulse is very small. And the variation in those pulses in well state of the human being or unwell state of the human being is very small. To measure those differences precisely, we need such kind of devices which can measure those values precisely. In another case, if you are going to measure the change in temperature precisely, then you have to use this particular instrumentation amplifier. So this is very much sensitive and very much applicable in the industry.